Good day, good evening, good afternoon, good morning, wherever you are in the world again, and welcome again to another stream on Freaky Physics. Today we will have CJ, and we will be again doing the same thing we were doing before, which is a paper one, and I'm gonna join the lesson now. I'm gonna join the lesson now, and hopefully he's already in. Um, well, he's not in yet. Uh, he did message me earlier that he said he's gonna be out. He has another lesson at the moment. So, okay. So while we're waiting, just a little bit of a reminder. We've been doing this for the past 3 lessons with CJ. We've been doing paper one practice, and we're not only going through how to properly answer them with the correct answers, but also a few techniques here and there to help you remember uh, either how to answer that particular problem or knowing what a good way to think of the problem is. Okay, so we're still waiting for CG to come in. Hopefully he's gonna be in soon. Okay, so while we're waiting, let me just check all my settings. Now, oh yeah, I'm not wearing my lab coat yet. Hold on, let me wear that. Again, for those who are not aware yet, this stream is brought to you by a new laptop. My old yeah, the old laptop still works, and it works pretty fine. However, its physical condition is in a very bad state, and I decided to convert that into a desktop. Um, okay, there we go. In case you're wondering how it's going, I am now figuring out how to turn it on without using the keyboard's power button. Um, I've seen a few videos that a lot of laptops, well, actually a lot of newer versions, maybe from maybe 5 years ago onwards, the power button is integrated into the keyboard, so it's really kind of hard to turn on a laptop in that case. But I have been looking at possible hacks on how to do it, and CJ is here, so let's welcome him.
Hi, Mr. Dennis.
Hi, CJ, how are you today?
I'm good. How are you?
Good, we're doing good. All right, so today we're gonna do an hour lesson, and from what I gathered, we're still gonna do paper one. Is that correct?
Yes.
All right. Okay, so um, last time we were doing paper one from time zone one. Okay, so just a few questions from there, and we started from the end of the paper, from the last question, and working our way up. Okay. For today's Jamboard, let me just share the link with you right here. Editor. I think I forgot to share with you the link last time.
Yeah.
Yeah. All right. I'll get to that one later, and I'll share it with you as well. Here is the link for today. All right. And can you see the whole board right now on the screen? Let me try
No.
writing something first. Okay, I think that's good enough. That's right at the edge of the board for me, so it should be good. Can you see that scribble I made
I can
over
see
there? All right, great. All right then, so let's start. Uh, okay, so we were done. The last question we did was about energy sources, which ones would be secondary energy sources, right? So let's move on to the next question here. Um, okay, so here's our first question of the day. Okay, so what's the energy equivalent of the mass of one proton? I'm gonna copy something from the data booklet that should be useful. This is in the um, data section, not the formula section. So one of these would be useful.
Mm, um, w- whichever one divides into 1.673 times 10 to the negative 27.
Okay.
So I don't
Mm,
think it's D
you
because that
don't.
one makes it so it's
Okay.
negative 11. So I'm looking for the right sig figs, right?
Right. You're right.
I mean, the right to the power to 10 to the power of negative 27.
All right.
So is
Okay.
that C?
Hold on. Before I tell you the answer, something else that would be useful is available in topic 5, I think. Yep. Let me see
Um,
if it's here. If it's not topic 5, then it's topic 7. No. No. Okay, it's topic 5. All right. Let me see what would be useful here. Oh, okay. It's not here. Ah, here. This is from topic 5. This is also going to be useful here. All right. I'm gonna. Can you tell me what you used? I think this is the more useful one here from this set of equation values, right?
mhm,
And then this would be useful here as well. Okay. So, okay, this is in terms of using the data booklet to help you answer. Because from here, this is going to give you that the work done, and that's equal to the energy gained, right?
mhm,
Is equal to VQ, right? So we're going to put that in here. Now you will notice that the proton's rest mass is given here, and the more important thing here that we need is that value, that 938 mega electron volts per c squared. So that already tells you that from there, that the energy equivalent of the proton's rest mass is equal to 938 mega electron volts. That's already the energy equivalent. But since the energy equivalent here is not in mega electron volts, but in joules, we need to convert this to joules, right?
mhm.
Okay, so well, if we look here, we already have our volts right there, right? So we need to convert that
Yeah.
E into coulombs to get joules. So what I'm gonna write now is that's gonna be equal to 938 times 10. Well, mega is 10 to the 6. Electrons is 1.6 times 10 to the minus 19 coulombs times volts, right? Okay,
Mhm.
so that's your E, and then just there's your volts. So there we go, and you can already see which one it is. The answer is
Um, you said it's it's D.
it's D. All right, correct. So that's the final answer on this. So that's so this is using the data booklet to help you out. You don't have to memorize any of this. Okay, right?
Mhm.
Okay, let's move on. Second question. All right, we have a question about nuclear fission and binding energies and stuff. Okay, so the question here is there. Okay, so there's the first question. There's a question here. So you have nuclear fission, and you have a nucleus of element X absorbing a neutron to give a nucleus of element Y and a nucleus of element Z. And we have that reaction. What's the magnitude of the binding energy per nucleon of Y to that of X, and the total binding energy of X and Y and Z to total binding energy of X? It seems complicated, but we can simplify this later. But go ahead, try to answer this first.
Hmm. It should be equal, right?
No, it shouldn't be equal.
So is right side more than the left side?
I'm gonna give you an idea. Remember in fission, yes, the total energy must be the same, but some of that energy is actually transformed into actual pure energy, right?
Mhm.
What are you doing? Okay, say hi.
Hmm.
Okay, yeah,
Um. Oh no.
okay. Well, at least what do you think is not the correct answer?
I also don't know.
Okay,
Y over X. Hmm.
remember
I
you
feel
start
like
with X and then you go, it changes into X and to Y and Z, right?
yeah, I feel like Y over X would be um oh less than one.
Mm-hmm. So you think it's either C or D, yeah?
No, yes, is it?
Okay. So okay, I'll just cross this out because that's actually correct. It should be less than one. But I'll explain it further later if you're still not clear on why. All right. I'm gonna
Because Y plus Z plus N should equal to Y plus Z should equal to no, I don't know why.
okay. Here's the idea. Before we go to actually selecting C and D, let's explain this now, right? Remember that this side of the equation and this side of the equation, there should be energy plus energy produced, right?
Hmm.
So in other words, the total mass here should be larger.
Yeah.
Okay. So the total mass here. So this means this is the only part with mass, only bit with mass. Okay, with mass here. And then this comes from E equals mc squared. So there's missing mass already. So if there's missing mass, then that means there should be,
Because missing mass.
if there's missing mass, then the total binding energy has been reduced. The binding energy,
Yeah.
the binding energy here. So the binding energy here gets transformed into binding energy here, plus this extra energy.
Hmm.
Okay, so what happens? So that's why it's either C or D now. Now let's take a look at this. I'm gonna ask you
I think
something.
that
Well, go ahead.
it's I think it's C because it says in nuclear fission. So I think
Correct.
it gets bigger. The
Correct.
magnitude gets bigger.
This is correct. Okay. Reason being, if you remember the binding energy curve is more or less something like that, right?
Hmm.
BE curve. So what does this mean? Remember, this is the BE per nucleon, right? And then in fission, always you go this way,
Yeah.
fission. So because that's the case, the binding energy per nucleon, this would be X here and this would be Y here. And therefore,
If it was fusion,
it
would it
will,
get bigger as well?
yes, it will still be greater because this time you're going this way, but you cannot remember there's a limit. This is the fusion section and this is the fission section.
Hmm.
So either way you go, the tendency is to go to that highest possible binding energy per nucleon.
Hmm.
So either way the answer would be greater than 1, whether it's fission or fusion.
Yeah.
Okay? Fusion or fission. Okay. All right, so I guess that's clear. So I hope that helps. Let's go to the next one. Um all right. Okay. I feel like I shouldn't be putting this in here because this is an outdated question, literally outdated by 2 years at this point. Okay, but let's just go through it either way. What's the definition of the unified atomic mass unit?
Oh, you showed me this.
Mm-hmm.
Um, um, 1/12 of the mass of a carbon 12?
But here's the
No,
thing: you have two carbon 12s. You have neutral atom, and then you have nucleus. So B and D are wrong, right? As according to your statement.
according to me.
Mm-hmm.
Uh, is it neutral? Nucleus, I mean nucleus.
Okay, the correct answer is A.
Okay, why? What does
Atomic.
neutral and nucleus mean? I thought it was supposed to be neutral either way.
No, the
I don't know.
nucleus here is just the nucleus, so this would be positive. This is just the neutrons
Oh,
and protons. Okay, this is the whole thing: neutrons plus protons plus the electrons. Now, by definition, well, the old definition at least, one atomic mass unit is 1/12 the mass of an atom, neutral atom of carbon 12. So you have to take into account the mass of the electrons as well. Okay. Now, having said that, like I said, this is an outdated definition, so I'm not sure if this is gonna be this particular question is gonna come up. But just in case it does, okay, that's the idea. It's always the atom. Okay.
hmm.
All right. What's the new definition? I'll just put it here just in case this question also comes up. This new definition came up uh, in 2019. Okay.
Hmm.
This is now defined. One atomic mass unit is exactly still 1/12. Okay. Um, oh, hold on. This is actually sorry. This still this new this is still the new definition, but something's different. Oh, okay. This is still the definition, but earlier the atomic mass unit defines Avogadro's number. That's the thing here. And A. Okay. Now it's the other way around. Avogadro's number defines the atomic mass unit. The atomic
Oh,
mass unit. Okay. It used to be the other way around. Okay.
hmm.
All right. So let's move on. Again, it's just something to know just in case a question comes up. All right. The next question we have here today is this. This is about radioactive decay. I think we can fit this here. All right. This is basically you should know this. You should try to memorize not this particular um reaction, not this particular decay, but um how you would look at the charges. Okay?
Hmm.
Okay. So first of all, um okay, go ahead. What do you think the answers are?
Good question.
Okay, look at their choices first. That means this must be the neutrino, neutrino or normal neutrino, right? And this must be the electron, whether it's positive or negative. So the only thing we need to know now is something. You can
Oh, it
actually,
gains a proton.
uh-huh, it
Or is it a
gains,
neutron?
it gains
A proton.
proton.
No, that's a neutron.
Yeah, it gains a neutron, so it loses a proton, right?
Yeah.
Okay,
So if it loses a proton, does it gain an elect? No.
okay. I'll give you
Does that
an
mean it's a
easier.
neutron?
Okay, I'll give you an easier
X
way
is a
to
neutron.
do it. Okay, instead
Yeah.
of thinking of neutrons, protons, and whatever, just look at the numbers.
No, it's decay.
Yeah, it's definitely a decay, but look at the numbers. This is 14, 15, and then this is 14. Remember, just like in chemistry, nuclear reactions should balance out. Both the nucleons and the proton number should balance out. Z and A. So this is
This
proton.
is beta positive.
Uh huh. So beta
Beta
positive.
plus.
So
Does that mean it's a neutrino and a positron?
neutrino and positron. Your answer is D. It's correct. Okay.
Okay.
All right. Great. So that's the idea first. So Z and A, the proton and nuclear number, must be conserved.
Yeah, what about the gamma?
Gamma,
What if it was a gamma?
gamma's 0, 0, so either way, it's still gonna be conserved.
Oh, so gamma doesn't really change anything.
Gamma doesn't change anything. Now, what exactly does it do? It just allows a highly energetic nucleus to emit extra energy first. Okay, so all right. So in this case, this is 15 here. This must be 15 in total. So this must be 1 and 0. So that's 1. That already tells you you don't even need to solve. Well, that's 0, 0 anyway, right?
Hmm.
Now, that means 1 positively charged. So it's a positron. So, and again, in beta decay, what happens? One antiparticle, one normal particle must be produced. So this is anti, right? So this must be normal. So which one is gonna give you that? It's only D.
Hmm.
All right, let's move on. Okay. Okay. This time it's about circular motion. Okay. This is Okay. I'm not gonna tell you anything on this one yet. I'll just present the problem, and then let's see if you can answer it. Just tell me if you need help.
Okay. Uh, okay. Um,
Mhm.
I feel like hmm, if you make the rope longer
Mm-hmm.
for some reason and make the speed mm, more,
Okay.
I feel like it will break easier.
Okay. This is an example of using logic first before any solutions, right? Your
Am I
logic,
wrong?
well, your logic, I'll tell you this much, your logic's correct.
Uh-huh.
Okay. The reasoning behind it doesn't matter at this point because it's an MCQ, right? But let's discuss
Yeah.
it either way. So what's your answer first?
Mm, uh, okay.
If you had to solve for this, then yeah, you really need the equations. But looking
Hey,
at your choices, there's only one possible
I don't know.
answer. That's correct. Okay. So
Okay.
let's discuss this briefly. Why'd you get that? You said because longer means faster motion, right?
Yeah, but why?
But why? Okay. Now remember, when it breaks, the idea here is the rope breaks uh, when tension reaches maximum possible value, right? Reaches maximum value. So what are you gonna do? Basically, you're gonna look for T max. Okay, and since you're comparing two things, you're gonna equate T max to itself. Okay, on the left side, we're gonna use this tension. Now, also one more thing. This is centripetal force, right? This is the only source of centripetal force, the tension. So what you can do is you can put the equation of centripetal force in it. This is going to give you mv squared over r equals, you now know, still the same mass. Then you're going to use a different value for v first, and then you're going to use a different value for, oops, a different value for r as well. So we're going to do that. So v squared over r equals v squared over r. Now, which one of these would give you here? Just put all of these one by one in there, and you will see that only A works.
Mhm.
Okay. So if that's the case, if we put A in, our rope length is now 4L, and this is going to change to L. Forgot about that, right? And then our new speed is going to be 2V squared. So what happens, that 2 and that 4 cancels out. We're left with the exact same thing. You put the other equations in, you won't get this formula. Okay. All right. So that's solving it. But actually just doing this particular bit on the logic is good enough. Okay.
Okay.
All right. Next. Oh, circular
Okay,
motion
instead of
again.
trying
Go
to do
ahead.
the math part, I'll try to logic it out because I
Uh-huh.
know I'm not good at math.
Well, a lot of the time you can actually use a lot. You can use logic as long
Okay, I'll
as
try
your
that.
yeah, as long as the math behind your logic's okay, or the idea behind the logic's okay, you should be able to answer it.
Okay.
Okay.
Uh,
Right. This one. Can you just use logic on this one again? I
okay.
think so.
Okay. Linear speed. Linear speed. Centripetal. Angular acceleration.
Mm-hmm.
Hmm.
Centripetal acceleration.
Yeah. Oh. Um. I feel like X is gonna be A because it's gonna be slower than Y
Mm-hmm.
because it's like longer. And when I see like objects further away from the middle, it
Mm-hmm.
like goes slower.
Uh-huh. You have to be careful here. That works if you're dealing with things orbiting something. But this is not orbiting a planet, right? This is on a disk.
Yeah.
So since this is a disk, I'll give you a bit of help here. Since this is a disk, they're rotating at the same angular speed. So which one is actually moving faster, X or Y?
Wait, you said they're both moving at the same speed,
At the
so
same
they're the same
angular
speed.
speed. They're rotating at the
Oh,
same rate.
then
Uh,
maybe X because it goes through more angles. No, it doesn't. Wait. Huh? Yo,
Angular.
well, which one? Which one rotates more?
Again, they rotate at the same time because they're on the same disk,
Yeah.
right? So when Y completes one rotation, X completes one rotation as well.
Mhm.
Okay. So
Oh,
which
X
one?
has acceleration of 2A,
Okay.
and its speed is the same.
Okay. That's not correct. So
Oh, is
you
it A then?
okay. The answer here, the linear speed. Okay, A and C are wrong.
Oh, so it's not the same speed.
Now think about it this way. This rotates once. This also rotates once, as I mentioned earlier, right? So if Y is half the distance from the center's X, then that means the let's write that here. The circle that X traces, okay, so
Is
X traces a
more
larger
distant.
circle.
Yeah.
Larger circle. Specifically, the circumference is
Double.
double, twice of Y, two times of Y, right? So same time, twice the distance, so twice the speed. Hence the answer is either B or D. Okay. Now for centripetal acceleration, this one's a bit difficult to reason out, but we don't have to fully calculate as well. We still do the math. So what's the math here? You're gonna have to use again. We're looking for acceleration only, and the acceleration is equal to v squared over r. Okay. Or
Mhm.
or this can also be equal to omega squared r. Now, here's the thing. Rotates at the same angular rate, same omega, right?
Mhm.
So which one's going to be more useful? It's going to be this. Since the omega is the same, but the distance is twice as much, then the acceleration is only twice as much as well. Okay, so the answer is B. You did say 2a for the acceleration. That's correct. Okay,
Okay.
but for the linear speed, it must be twice as fast as well. All
Yeah.
right. Okay. So this, you really have to look at the formula booklet here. Okay. All right. Moving on. Okay. This is now electricity. So you have a cell connected to circuit components. Okay. Okay. 500 seconds. All right. Should be easy enough. Okay. 1.5 kilojoules of energy is dissipated in the cell and 2.5 kilojoules of energy is dissipated in the resistor. So it's the EMF of the cell. Ah,
Hmm.
I think you. This is one of those cases you have to calculate.
Yeah. So EMF equals I big R plus small r.
Mm-hmm. Correct.
Um, A, we have the T. Wait,
Okay.
huh?
Okay. I'm gonna tell you this much real quick. Okay.
Yeah.
Uh remember that power equation that involves
Hmm.
resistance and current.
Energy over time.
This is the definition of power, but there's another one that involves um
Work over time.
cur- no current. It involves current and
Oh,
resistance.
I squared R.
I squared R. Okay. Now, so what can we do?
Wait, so does uh
Remember, there's one more thing you need to look at. They're in series. So that means the current through either one must be the same.
yeah.
Mm-hmm.
So do I just get rid of it? Wait, no, 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 I don't.
Okay, I'll give you one more clue.
Wait,
You can use a ratio.
can I do it's a ratio?
Mm-hmm.
Yeah. Can I plug in 500 seconds and then
You
I don't
could, but
know.
that's actually gonna make it longer. You could, yeah, just so we're clear. But I
Oh,
personally wouldn't do that. It's gonna remember. Okay, I'm. Here's something. I just mentioned this to my class one time. Okay, so again, whenever you're doing any sort of work, it's always a much better idea to work with the formulas and cancel stuff out first, rather and then look for the thing you're actually looking for, rather than plug in, solve. Then later on, you'll cancel them out again anyway, and then you find the answer. So start with the formulas and cancel stuff out first. Okay.
mhm.
So, okay, how am I gonna start with that? I'm gonna go start with this.
Can we cancel the I's?
The ice can be canceled, correct? What else can be canceled?
Um,
Okay, here's the
yeah.
thing. This I think I'll show you how to do this now. Okay, but I think you get the idea. But I might as well just show you. So I'm gonna start with the energy. I'm gonna rewrite that formula into energy equals I squared R T, right? Here's the thing. You're given the energies for the two things. So you're gonna have energy of the cell, okay, over energy of the dissipated by the resistor. right? So what am I gonna do now? It's gonna be I squared in R, internal resistance of the cell would be small r, right? Then T over I squared big R T. What cancels out? I squared cancels out. T
And
cancels out.
T, yeah.
Okay. So, all right. So from here we can see that the ratio between the resistances would be 3 to 5. 3 to 5, right?
Yeah.
So, okay. So from here we know that and then we're going to focus specifically on this bit, that the ratio of the resistances should be equal to that. Now, what happens next? You're going to have to actually find the uh what's this? You're going to have to find we're looking for the EMF, but we know the current, right? Okay. The current is 4 amps. Okay. And then we can find um okay, what's going to be the easiest way to do it here? All right. So I think the easiest way to do it here is to do um this is going to be the case. From this ratio we're going to get R is equal to 3/5 of big R, right? Then we're going to plug that in there. So that's going to be EMF is equal to I times uh R is R, then 3/5 this is the 3/5 R. So that's going to give us finally 3 no 5, that's going to be 8/5 R. Okay? Now, the next thing here is we don't know what R is, right?
Hmm.
We don't know what R is, but we know the I. We know the I. It's 4 amps. So finally, gonna get EMF is equal to 32 over 5 times R, right? Now, which of these we're not quite done yet. We need okay, let me just check, see if there's a faster way. All right, in this case, this seems to be going nowhere because of that big R, right?
Hmm.
We need to find, oh, okay. How can we find big R? We're gonna use this and this and this, okay? So to find big R, we're gonna use this. So big R will be equal to energy divided by I squared times time, okay?
Yeah.
All right. So what's the energy here? That's gonna be 2,500 over 16 times 500. 500, this becomes 5. So we're gonna put this now. This is gonna become 5 over 16. What happens? That 5 cancels out. This cancels out, gives you 2. There.
This is
Final
looking for the big R or the small R.
big R.
Okay.
We can actually use the small r either way, okay?
Hmm.
All right. So anyway, what happens is again, um, see, we don't even have to solve for the actual value of the r yet from here. We just put it in as the fraction so we can cancel stuff out more easily. So our answer is D. Okay. All right. So again, let me redo that step by step, but much quicker, so we can solve it. So we can see again how it's done. Okay. So first, okay. So it's the first one. Um, we're gonna do E equals power times time, and that's gonna be the power is equal to um I squared R. That's a power times T, right? So, so we know that the energy of the big resistor will be equal to 4 squared R times 500. Um, and we know also know that's 2,500. Okay, so E on big R is equal to 2,500. So from here, we know that big R is equal to 16. Sorry, the other way. 2,500 divided by 16 times 500. Cancel that out. Gives you 5 over 16. Okay. Again, no need to actually solve. Keep it as fraction. The second bit is we're gonna use the same thing. Energy equals I squared R T. So we're gonna do R over energy of R. Then we're gonna do equals I squared R T. The i's and the t cancels out. That's gonna become 2.5 over 1.5. That's gonna give us 5 over 3. We did it the other way around earlier. So we did R, big R on top, right? So let's just keep it consistent from before. This is big R, this is small r. So we just change this. This is 1.5 and this is 2.5.
Mm-hmm.
So this is gonna give us 3 over 5. So from here, and that's equal to big R over small r. Then we use this and plug it in here. Okay. Then finally, we do EMF equals big I times R plus R. Uh, we substitute stuff in. This is gonna be 4. Our big R is 5 over 16. And then our small r is plus. Okay. Well, that's the idea. Hold on. Getting. Let's just redo that first. So big R is 5 over 16. And small r would be. Um, okay. Over 16 over r. Okay. So from here, we can get r is equal to. I'll just do this here. R equals. Uh, yeah, 3/5 of 5 over 16. Cancel out. We get 3 over 16. Plus 3 over 16. That's going to give us. The 4 cancels that out with 4, right? And then we get 8 over 4. We still get 2. Okay. All right. Again, I think this is one of the harder problems in the paper. So if you miss it, it's fine. If you can get it, that
Yeah.
means you're worthy of a 7. Okay.
No, I'm not gonna get.
Oh, by the way, did your teacher give you a predicted grade yet?
Yeah,
What was it?
4.
4. Um, you think personally you can get a 5?
No.
I think you can if you study a bit harder. But right now, from the way you're answering, yeah, I think you'll be a 4 at the moment.
Yeah.
Okay, but 4 still better from when you started, right? From when we started
Yeah.
together. All right, so let's move on. We have an electron accelerating through a potential difference of that. What's the change in the kinetic energy? I think you'll need something from the data booklet. Let me look for
Oh,
that.
the what's it called? The size, the multipliers, the metric
Yeah,
SI multiplier.
yeah, that's one, and you'll also need this. Okay, so hold on, I'll get the multipliers from the data
But yeah,
booklet.
what equation to use with a potential difference?
V, anything with V would be useful.
Okay. Also, the V equals W over Q equation is kind of hard for me.
Okay, so we'll go through that later after we go through this problem. Okay, so when do you use that V equals W over Q, right? All right, so,
Mhm.
all right, going back here first, what's the answer? Okay,
Oh.
okay, I think I'll make the prefixes a bit bigger here so it's easier to read. Mega and change in the kinetic energy of the electron. You'll also need a value. I think you've kind of memorized that value, but I might as well just put it up here. Where is it? The charge of the electron, the elementary charge. You'll need this.
Yeah, so 2.5 times 1.6
Mm-hmm.
times 10 to the negative 19.
Mm-hmm.
Hmm. But MV. Hmm. So it's 10 to the 6.
Uh-huh.
2.5 times 10 to the 6 times 7.6 times 10 to the negative 19.
2.5, 10 to the 6, 1.6 times 10 to the minus 19. Gives you what?
0 0.4 something. 0 0.4 19 minus 6, 13. Maybe it could be
Okay.
a PJ, but I think
Okay. What about this? This
P
would give you how much? 4,
0.4.
right? Just actually
Oh,
4.
4?
So,
Just 4. Okay.
yeah. So, here's the deal. You want to turn that into
0 0.4?
0.4, right? So, that's going to be 0.4 times 10 to the minus
14.
no, 12.
Oh.
Okay. Why do I know it's 12? Because I know, look at our values here. Beyond 3, it's always 3, 6, 9, 12, 15. Same thing
Mm-hmm.
here. Beyond 3, we have 3, 6, 9, 12, 15. It is all the prefixes always increase the value by a factor, or not a factor, by a power of 3.
Oh, so it's C then.
So it's C because minus 12, right? So pico. Correct. Okay. So that's something that would be very helpful later on when you're doing these kinds of conversions wherein you're looking at prefixes. Always remember that beyond centi and beyond hecto, they are all powers of 3.
So the
The
whichever one's the closest.
Yeah. So in this case, yeah, you have to convert this 13. This could You could convert this into either negative 15 or negative 12, right? But if you put it to negative 15, then this becomes 4, then I add two zeros, right? And then if I
Mm-hmm.
convert it to negative 12, that's when it becomes this. And then negative 12, as you mentioned here, is pico, so that's why the answer is C.
What if it was negative 11? 4. 4
Ah,
times 10 to the negative 11.
all right, let's do to 10 to the negative 11. So let's say the answer is negative 0.4 times 10 to the minus 11, right? So again, you could do either one. You could do either 10 to the minus 12 or 10 to the minus 9. If this is 10 to the minus 12, this becomes 4 point. Sorry, let's not do 0.4. Let's use 4. So this becomes 40, right? And then this becomes 0.04. So the best answer given here, let's say that you're supposed to have 0.04 on all your choices, then the answer would be minus 9 is what? Nano. Okay. So this would
Okay.
be,
So you have
okay.
to go down.
Yeah. And then this is going to be 40 after nano is pico, right? Let's
Mm-hmm.
put meters here. So picometers, nanometers here. Okay. All right. One thing that you were asking before we do one more problem, okay, is you said that you're still having problems with what this means, right?
Yes.
I also would assume that this can confuse you because they kind of look the same, right?
I only
So,
know that we use that one to like can't like to combine it with the first equation.
mm-hmm,
I mean the second equation.
the second equation, correct? Okay, so let's just go through that briefly and let's just note what all of these mean. Okay. All right, so let's put this here and let's focus on those two. So this one is potential difference. This is the definition of potential difference. Okay, this is by definition, and that means that's equal to work done on charge, right? Divided by
Mm-hmm.
magnitude of charge. Now, also this also means you can say that as energy gained or lost, right? I'm just gonna use gained, but you can use this equally for lost. Okay, over charge. Okay, what does this one mean? This is electric field. The definition of electric field.
Mhm.
Of electric field. Electric field. And that's equal to force exerted on charge, right? Force on charge divided by magnitude of charge. Okay, so keep just be sure you can, I know you can distinguish between the two, but remember these are the definitions. So you can't really do anything else with these but follow them. Okay.
Mhm.
All right. Okay, last question for today. Well, okay, we are about halfway through the paper that we're looking at. So I think we're good at the moment. Yeah. Okay, so last one. All right, so we have a graph showing the variation of current with potential difference on a filament lamp. What's the resistance of the filament when the potential difference across it is 6 volts? Okay, I think I better discuss this briefly afterwards because a lot of people still get confused over what to use. 6 volts.
Mhm.
Should I make the graph
D equals
bigger? Or at least you can
R equals
guess.
V over I. R equals V over I.
Mm-hmm.
Equals V over I.
You're correct. V
But this
equals.
one implies that. Wait. So
Uh-huh.
does that mean it's 2/6 if it's V over I?
No, it's not 2 over 6.
6 divided by 2. So it's 3 for there.
But look at your
When
choices. You
it's
don't even have something with 3 in it, right?
when it's 6 volts is um
Okay, we're 6 volts.
wait. 6 volts it is 9 divided by 6. 1.5. No.
No, it's not.
Is it A?
No, it's
No.
not A.
3 ohms. C. If it's not C, I'm crying.
Okay, it's C. Okay.
Yay.
Okay, let's go through this briefly, okay? You were right to say that R equals V over I. That's right.
Yeah, but then the graph shows otherwise.
No, actually, it's okay because here's the thing. It does not say change in V over change in I. In other words, whenever you have a potential difference graph, use the values straight away. You don't have to overthink a potential difference to current graph.
Hmm.
Okay.
Oh, okay.
Okay. This will work if you're looking for a gradient, right? But as looking at the equation, resistance is not a gradient equation. It's a values equation. In other words, we use the value straight away here, right? And as you said, this is 9 and that's 6. So all I'm going to do now is plug the values in. V is 6. Look, V is 6, right? Over
Hmm.
I, 9. But milliamps, so 10 to the minus 3. So that's going to give us 6 over 9 times 10 to the 3. I already know that 6 over 9 is going to be 2/3. One that has 2/3 in it, C.
Hmm.
Okay. So there, that's the idea. So again, yeah, I really wanted to discuss this bit because I know a lot of students get confused when it comes to graphs for this. So again, I want to remind you, do not look for a gradient in a potential difference versus current graph. Okay,
Yeah.
the gradient doesn't get you anywhere. You use the gradient for anything else like speed, acceleration, those
Mm-hmm.
things where changes are needed. But if the change isn't needed, it's just the values like this. Just use this straight away. Okay.
Okay.
All right. So we started from number 30 last time. We are now at number 18. So we finished how many total? We finished 12 already out of 30. So
Okay.
next meeting, I think we can finish the rest of this paper and then we can work on something else as well. Okay.
Okay.
All right. So speaking of next week, so not next week, next meeting. I'm looking at the timetable. It's correct. We're doing a 2 hour lesson then, right?
Thursday, yeah.
Thursday. All right. Okay. So in that case, we can end that then, and we'll just meet then on Thursday. Hopefully, we can finish all this by then and start a new one. Yeah.
Mhm. Okay.
All right. Okay. So all right. So good night then, or good evening, and I'll see you next time.
Good
Bye,
evening. See
CJ.
you. Bye
Thank
bye.
you. Bye bye now. All right. So that's the end of the lesson. So let's go back to the stream. Right. So yeah. So hopefully, for those who would be listening into this or trying to learn from this, again, those are some of the things you need to know or at least try to apply. Okay, so just make sure that when you do these things in the actual paper, I'm pretty sure some of you will not remember everything. For those who would, then that would be great for you. But if you don't, it's fine. Remember, our goal is to pass. If you can get a 7, you wouldn't be listening into here anyway, right? Yeah, I'm kidding, I'm kidding. But yeah, whether you're aiming for a 7 or just going for a 4, I hope this really helps you. Uh, but the idea still is there's always a way to think of a problem to make it easier to solve. Okay, especially the harder ones. So I'm trying, what I do here is I try to give you all the possible techniques and stuff to remember that's not taught in the textbook. So just make sure that you're careful with that. Okay. So before we end for tonight, so again, I want to ask you all to like, share, and subscribe to the channel, um, wherever the channel is. Oops, let's adjust that a little bit. There we go. So again, don't forget to like, share, and subscribe to all the channels on Facebook, YouTube, TikTok, Instagram, and Twitch. We stream on Twitch, Facebook, and Instagram, and announcements are done on Facebook, Instagram, and on TikTok. I haven't been able to do announcements recently because quite busy with work, real life work. But once I've finished everything, we should be fine. Right? So I think I can start updating this week. Um, Same thing, my editor. He's been waiting for something to do, but yeah, I'll probably give him something to do this week as well. All right. So with that, everyone, again, don't forget to do all the things I just asked you to do. Like, share, and subscribe to any of the social media platforms here. Let me adjust that real quick. So with that, I bid you all again a good night, good day, good morning, good evening, good afternoon, wherever you are in the world, and stay freaky, everyone. Adios.